So, in the first video about NMR, we have seen some theoretical aspects, and we have also seen that when you place a sample where you have different nuclei that present a magnetic moment, and if you place this sample in an external magnetic field, you will generate two energy levels that are characterized by a certain population in each level. First thing, it's clear that when you have this external magnetic field, the ratio of the population in the two levels will be different to 1 and not to 0. Sorry, in the previous video, at the end of the video, I said 0, but of course it's a ratio that must be different from 1. You see that the ratio is not so different compared to 1, but it's different, and that means that the population in the two energy level is different. And due to this difference in population in the two energy level, you will observe a global magnetization. Another thing that I have to say is that here in the Boltzmann equation, K, it's the Boltzmann constant, and T, it's the temperature, of course. So we have seen that we have macroscopic magnetization, but now how can we use that to extract some information about the protein structure? So to observe something, you will have in fact to switch on a second magnetic field. So what we did up to now is to generate two energy levels, two states, with the static magnetic field B0. What we will do then is to irradiate the sample at a frequency that is close to the Larmor frequency, with the objective of generating now transitions between the ground and the excited states. And how do we obtain that? We'll obtain that by switching on a second magnetic field, B1, and this second magnetic field must be orthogonal to the direction of the first magnetic field, B0. In fact, here you have several ways to work. You could irradiate at a frequency that is close to the resonance frequency of the different nucleus in the sample, and you could scan at different frequencies. That's a first possibility. But in general, what we will do is to work with a very brief pulse of B1. So we will not test all the possible frequencies, but we will work with a very short time pulse, and doing that you can scan a broad spectrum of frequencies and obtain an excitation of all the nuclei. What is the result of this pulse of the B1 magnetic field? The result is that you will switch the magnetization in the XY plane. So thanks to this second magnetic field, and thanks to this pulse, you will switch the macroscopic magnetization, and the X and Y component of the vector magnetization will, in the XY plane, will be different from 0. After that, you will switch off the B1 magnetic field, so it's very short pulse of B1. And after you will switch off this second magnetic field, the global magnetization will come back, will reorient again along the z-axis. And so the magnetization will tend toward the MZ, the z-axis component of the macroscopic magnetization. And after that, Mx and My, the X and Y component of the magnetization, will tend towards 0. And what we will do in NMR, we will follow the evolution of the magnetization along the X, Y, and Z axis, and we will follow what is called the relaxation of the system. Here, just for your information, but we will not detail that in the course here. There are mainly two time constants that are related to this relaxation process. T1, which is called the spin lattice relaxation, which will measure the return to MZ, and T2, which is the spin-spin relaxation, which will measure the evolution towards 0 of Mx and My. But we will not detail this information here. So, something that is important here is that you have thus this perturbation. You will switch on the B1 magnetic field. This will induce the perturbation in the system. This will induce the switch of the macroscopic magnetization in the XY plane. You then switch off the B1 magnetic field, and you will measure the return to the equilibrium. What is important also is the frequency of resonance of the different nuclei. Here, if we work with hydrogen 1, for instance, it will depend on the environment of the different nuclei. We have already seen that if we apply the B0 magnetic field, the B0 magnetic field is not directly felt by the different nucleus, because you have a shielding by the different electrons that are in the surrounding of the nucleus. And so the magnetic field that is felt by the different nucleus, if we focus on its strength B, it's equal to B0 times 1 minus sigma. And as we have seen previously, sigma represents the shielding and is about 10 power minus 6. So here you see that according to the surrounding, you have a magnetic field that is felt that is slightly different due to the presence of the electron. And so the frequency of resonance of the different proton, of the different H1 hydrogen 1 nuclei is different according to the surrounding. And so you see that according to the value of this frequency of resonance, you could obtain information about the neighborhood of the different hydrogen nuclei. And this is important because that means that what you will finally measure is in fact related to the neighborhood of the different nuclei. And so you can obtain information about this neighborhood, and so information about the structure. And that is really important. Another important thing is that, in fact, this sigma, which represents the shielding, is very small. It's about 10 power minus 6. So it is thus very important to have a very homogeneous magnetic field B0, because if you have something that is inhomogeneous, the difference that you will measure locally could be similar. The amplitude of the difference that you will measure could be similar to the value of sigma. And so it's really important to have a very homogeneous magnetic field, B0. So what you measure is a direct consequence of the neighborhood of the different nuclei, and not a consequence of the inhomogeneity of B0. So here, according to the type of impulse, so we have seen previously that you have a pulse of the B1 magnetic field, so you will switch on and switch off the B1 magnetic field. And according to the type of pulse of B1, you will observe different behavior, and you can have access to different types of information. So according to the pulse, you will have different behavior and different types of spectrum. So in 1D NMR, you have mainly two steps. A first step, which is the preparation. And in this case, it's, for instance, a pulse of 90 degrees of the B1 magnetic field. It's here. And after that, you have the relaxation, you have the detection phase, where you will detect. And what you obtain is finally a spectrum. The different peaks that you have here are related to the represent, in fact, they are not related, they represent the frequency of resonance of the different types of nucleus. And as we have seen, the reason why the frequency of resonance is different, it's due to the fact that the neighborhood of each nucleus is in fact different, because you have in your molecules different distribution of the electrons. So here each peak will reveal one hydrogen 1 nucleus, and the value of the resonance frequency is different because you have a distribution of electrons that is different from one nucleus to another. Okay, so I could obtain such a spectrum for a protein, but the problem is that in the case of a protein, you have a huge number of hydrogen 1 atoms. And the results of that is that the number of peaks that you will obtain for a protein is very, very large, and the spectrum you have to analyze is really complicated. So here you have an example of a spectrum for a small organic molecule, but for a protein it's even more complex. So exploiting directly 1D NMR for 3D structure of proteins is not so easy. And so here you have to know that there exist other types of protocols. You have, for instance, what is called 2D NMR. In 2D NMR, you have a different impulse sequence. So here in this example, you see that you have a first preparation phase, then a first pulse here, an evolution, and after that a second pulse, which is called here the mixing time, and after that you have only the detection. And with 2D NMR, you can obtain such a spectrum here. And in general here, using these types of approach, by using these types of approach, it will be easier to detect nucleus of hydrogen 1 that are in contact in protein. So these types of spectrum is easier to interpret for obtaining the 3D structure of proteins. And so here, what we can finally obtain are distance constraints between the different hydrogen 1 nucleus or other nucleus that are present in protein and by which that you can use to do NMR. You could do that, of course, for with other types of nucleus. So here, the idea is not to detail this part, but keep in mind that so here we have just the general principles. And finally, with these types of protocols, you can finally obtain information about which atoms are in contact in the 3D structure of the protein. And so here you have different types of experiments. The names of these different types of experiments are, for instance, TOXI or NOISY. And these experiments will reveal some coupling between residues, and from this information you can finally obtain information about which atom is in contact to which atom. So you have information about the residues that are in contact in the 3D structure. So finally, the information that you obtain is a list of the amino acids that are in contact in the 3D structure of the protein. Finally, when you have this list of contacts between the residues, what you will have to do is to build a model of the 3D structure that is in agreement with this list of contacts. So you have, in fact, some distance constraints between amino acids, and you will finally try to build a 3D model that is in agreement with this list of distance constraints between amino acids. Some information that are important for that, you have to keep in mind that here you take this spectrum on proteins that are in solution. And so you have to keep in mind that all these proteins in solution, they are not rigid. They are, of course, they present a certain degree of flexibility. And the regions that are more or less flexible in the protein are in fact, the region, you have in fact some regions that are in the protein that present a low degree of flexibility, and other regions of the protein that present a larger degree of flexibility. Typically, the N-terminal and the C-terminal regions are in general more flexible. You have also the loops that connect the secondary structure. They are also a little bit more flexible. And if you have more flexible regions in this protein in solution, of course, for these regions that are less flexible, you will obtain a lower number of distance constraints. And so when you build a 3D model from this list of distance constraints, you have some regions where you have a lower number of constraints. And so for this region where you have a lower number of constraints, you could have more 3D structures that are in agreement with these constraints. So for instance, if you have a look at a 3D structure obtained by NMR, in general, what you find in the PDB file, it's not only one 3D model, but several models. So here in this example, you see that you have 25 different models. And if I go from one model to the other, you see that, you have some differences between them. You see that here you have small differences between the models. You see that in fact the structure of the secondary structures are quite similar, but you have some variation in the loops or in the C or N terminal of the protein. And so, in general, you have several models that are in agreement with the 3D constraints that you obtain from the NMR experiment. Okay. Okay, so that's something that is quite important here, is that you have several models for one NMR experiment. Okay, so that was for NMR, and in the next videos we will see other techniques that can be used to obtain information about proteins.